Welcome back to the deep dive. Usually when we meet here, we're dissecting a really specific slice of the world, like a corporate collapse or a historical battle, maybe a new tech trend. But today,
Mhm.
today we were doing something fundamentally different.
Yeah, we aren't looking at a slice today. We are looking at the entire pie.
The whole bakery, really.
Exactly.
We are taking this massive stack of encyclopedic entries. I mean, we've got sources here that span physics, chemistry, geology, materials science, and we are going to attempt to decode physical reality itself.
It's a pretty ambitious mission for a single deep dive.
It is, yeah. But our goal is to figure out what the universe is actually made of, from the absolute bottom up.
Because it really is the ultimate question of architecture. How do you take the smallest, most invisible things imaginable and arrange them to build, mountains, oceans, smartphones, and human beings?
Right. We are going to zoom all the way into the subatomic level and then zoom all the way out to the size of a cathedral. But before we get into the quarks and the giant crystals, I wanted to start with a physical reality check for you, the listener. If you're listening to this right now, I want you to just look at your own hand.
Or the desk in front of you. Or the steering wheel if you're driving.
Yeah, exactly. Look at the phone you're holding.
It looks incredibly solid.
It looks perfectly solid. Like, if I knock on this wooden table here, it stops my hand, it makes a loud noise, it feels like a continuous, impenetrable slab of matter. But according to all the research we have in front of us, that solidity is basically a hallucination.
It is the most convincing illusion in the universe.
It really is.
If we could actually see reality as it is, like if we had eyes that could see all the way down to the atomic level,
Right.
you wouldn't see a solid table. You would see a frantic, buzzing swarm of emptiness.
And the sources use this stadium analogy to visualize this emptiness. I think it's probably the only way a human brain can really grasp the scale we're talking about here. Walk us through this stadium idea.
Okay, so imagine we take a single atom, just one fundamental building block of that wooden table, and we blow it up until it is the size of a massive professional football stadium.
Like a massive Super Bowl-sized arena.
Right, a giant stadium. Now, we are looking for the nucleus. That's the center of the atom where almost all of its mass lives.
Oh.
In this stadium-sized atom, the nucleus would be a single marble sitting right on the 50-yard line.
A single marble
Just a marble on the grass.
in the middle of an enormous stadium.
Yes. And the electrons, the particles that actually define the outer physical edge of the atom, they would be these tiny specks of dust buzzing around the very top row of the nosebleed seats.
Wait, so everything between that marble on the field and the dust way up in the nosebleed section is just nothing?
It is empty space. The vast, vast majority of an atom is pure emptiness, which means, by extension, the vast majority of you is emptiness.
See, that is existential dread just waiting to happen.
It is a little unsettling when you first think about it.
But if it's all empty space, why doesn't my hand just pass straight through the table? Why don't I fall right through the floor?
Because you aren't actually touching stuff. You are interacting with forces.
Okay, break that down for me.
So the electrons in the atoms of your hand have a negative electrical charge. And the electrons in the atoms of the table also have a negative charge.
And negative repels negative.
Exactly. As you push your hand down, those magnetic fields repel each other with absolutely incredible force. It's exactly like trying to push two really strong magnets together, North Pole to North Pole.
They never actually touch. They just slide off or push back.
Right. They never touch. You aren't feeling physical matter hitting other physical matter. You are feeling the resistance of electromagnetic fields pushing back against each other.
So we are basically just force fields pretending to be solid objects.
That is the physical reality, yes.
That sets the stage perfectly for where we're going. Our roadmap for this deep dive is to decode that emptiness. We are going to start in the microworld, atoms, protons, quarks. Then we'll look at the social life of atoms, how they bond to survive.
Which is really the basis of all chemistry.
Right. Then we'll move to states of being, why some things are invisible gas and others are solid rock. We'll decode the periodic table, and finally we'll see how this all builds up into the macro world of geology and crystals.
It's a massive journey from the invisible to the monumental.
So let's start at the absolute bottom. Section 1, the anatomy of the atom. We probably need a working definition of matter first.
Yeah, the scientific definition is actually very broad. Matter is simply anything that has mass and takes up space.
So air is matter.
Air is matter. Water is matter. The sun is matter. You are matter.
And the Lego brick concept is the standard way this is taught in schools, right? Atoms are the individual bricks. But the scale of it, the sources mention that a single grain of sand contains trillions of atoms.
Trillions. It's one of those numbers our brains just aren't equipped to actually visualize.
No, not at all.
But the Lego analogy actually breaks down slightly when you look closer, because Lego bricks are solid plastic all the way through. Atoms, as we just established with the stadium, are not solid. They have internal machinery. We mentioned the nucleus earlier, the marble on the 50-yard line.
This is the trinity of particles, right? Protons, neutrons, and electrons.
Right. Inside the nucleus, you have protons, which carry a positive charge, and you have neutrons, which are completely neutral. They have no charge at all. And then orbiting way out around them are the electrons, which are negatively charged.
Now, here is the part of the reading that I found most mind-bending. It's about identity. Because physically, protons are all exactly the same, aren't they?
They are completely identical. A proton in a shiny bar of gold is physically indistinguishable from a proton in a breath of oxygen.
So the only difference between a heavy, valuable metal and a gas that we breathe is just the count.
It is strictly a numbers game. This is the whole concept of the atomic number. If you bundle exactly 6 protons together, the laws of the universe basically dictate you are now carbon.
You are a solid. You are a black soot or maybe a diamond.
Right. You are stable. You are the basis of all known life.
But if you catch just 2 more protons and shove them into that exact same bundle, bringing the total count to 8.
You are suddenly oxygen. You are a gas. You are invisible. You are highly reactive, and you help ignite fires.
That is just wild to me. Just adding mass changes the fundamental nature of the reality. It's not just heavier carbon. It is a completely different element with entirely different rules.
Precisely. The number of protons is the sole determiner of elemental identity.
So what do the neutrons do then? If they don't change the identity, are they just kind of dead weight in the nucleus?
Not at all. They are the peacemakers. Think about the charges. Protons are all positively charged. What happens when you put a bunch of positive magnets right next to each other?
They repel. They push apart violently.
Violently.
Yeah.
So if a nucleus was made of just protons, it would blow itself apart immediately. The electromagnetic force would just shred it. The neutrons act as a buffer.
Like a sort of nuclear glue.
Exactly. They space the protons out just enough to keep the nucleus stable. But the interesting thing is, the number of neutrons can actually vary without changing the element's identity. And this brings us to isotopes.
Isotopes. This is one of those words I usually just gloss over when I read science news. But the source text uses a car analogy for this that actually made total sense to me.
It's a great analogy. Think of the element, let's say carbon, again, as a specific model of a car, like a Honda Civic. To be a Honda Civic, it has to have the Honda chassis. That is the 6 protons.
Got it. 6 protons equals a Civic.
But you can get a Civic with a standard trunk, or you can get one with a massive heavy spoiler and a huge roof rack. It is still a Civic. It drives like a Civic, but it's heavier. That is the isotope.
Okay, so carbon-12 is the standard model. 6 protons, 6 neutrons.
Right. And carbon-14 is the heavy model. 6 protons, but 8 neutrons.
And that extra weight actually matters, right? Because carbon-14 is radioactive.
Exactly. Because sometimes the car is just too heavy. The nucleus becomes physically unstable because of those extra neutrons crammed in there. It wants to shed that extra weight to get back to a comfortable, stable state.
And that shedding process, that's radioactive decay.
That is exactly what radioactive decay is. When scientists date ancient fossils using carbon-14 dating, they're basically just measuring how many of these heavy cars have managed to shed their extra weight over thousands of years.
That makes so much sense. Okay, so we have the nucleus figured out. But the sources go even deeper. They zoom in inside the proton itself. Because for a long time, humanity thought protons were the smallest possible things, didn't we?
We did. We thought they were the fundamental, indivisible pixels of the universe. But when we started smashing them together at incredible speeds in particle accelerators, we found they actually broke open. Inside a proton, there are even smaller particles called quarks.
Quarks. And they are held together by something with a great name. I love that so much. They literally glue the quarks together.
Scientists are very literal when they have the opportunity to be. A proton is actually made of 3 quarks. 2 up quarks and 1 down quark. They are vibrating frantically inside there, held together by these gluons.
But here is the really mind-blowing detail from the reading that you alluded to earlier. The mass of the quarks themselves is tiny.
Minuscule. If you somehow weigh the 3 quarks inside a proton, they only account for about 1% of the proton's total mass.
Wait, if the physical ingredients only weigh 1%, where does the other 99% of the mass come from?
Energy. Pure energy.
How does energy have weight?
Well, the gluons are zipping around inside the proton at the speed of light. binding these quarks together with unbelievable force. That kinetic binding energy actually has weight. This is Einstein's whole E equals mc squared equation in action. Energy and mass are interchangeable.
So when you step on a bathroom scale in the morning, 99% of the number you see isn't actually stuff.
No, it is the kinetic energy of the subatomic binding forces holding your atoms together.
So we are quite literally just bundles of trapped energy pretending to be heavy objects.
That is exactly what you were looking at in the mirror. Trapped energy.
Okay, let's step back out of the nucleus, back out to the nosebleed section of the stadium, the electrons. The source material refers to this as the onion model.
Yes, and this is crucial because while the nucleus gives an atom its mass and its identity, the electrons determine its behavior.
How it interacts with the world.
Exactly. Electrons live in shells around the nucleus, like the layers of an onion, and there are very strict mathematical rules for these shells.
It's described like a VIP club with strict capacity limits.
That's a perfect way to put it. The innermost shell, the exclusive VIP room right next to the nucleus, can only hold 2 electrons. Once it has 2, the bouncer steps in. It's full.
And the next shell.
The next shell out can hold 8. And the one after that holds 8, at least in the simplified model we use for basic chemistry. And the thing you have to understand is that atoms are absolutely obsessive-compulsive about these shells.
They have deep anxiety about empty seats in their clubs.
They really do. This anxiety is the driving force of the entire universe of chemistry. Atoms desperately want their outermost shell to be completely full. If an atom has a full outer shell, naturally, like helium or neon, it is happy. It is completely stable.
It just ignores everyone else.
Right. It doesn't need to interact. We call those the noble gases.
Because they don't lower themselves to interact with the commoner elements.
Exactly. But most atoms aren't noble. Most atoms have, say, 7 electrons when they desperately need 8. Or they have one single electron dangling alone in a new shell. This creates a severe chemical hunger. They are desperate to fill or empty that shell, and they will do anything. They will explode, they will burn, they will bond, just to fix that imbalance.
And that hunger leads us perfectly into section 2, the glue of the universe, chemical bonding.
If atoms didn't have this electron anxiety, they would just bounce off each other like microscopic billiard balls forever. There would be no molecules, no water, no rocks, no life. Bonding is simply atoms trying to solve their electron problems together.
The outline highlights 3 main types of relationships here. Let's break them down because the personalities involved in these bonds are really distinct. First up is ionic bonding. I called this one the transaction.
It's a very dramatic transaction. The classic textbook example is table salt, sodium chloride. To understand why this happens, you really have to look at the individual players first.
Okay, let's look at sodium.
Sodium is a soft metal. It has exactly 1 electron in its outermost shell. And it absolutely hates this electron. It makes the atom wildly unstable. If you take a chunk of pure sodium metal and just drop it into a bowl of water, it reacts so violently to get rid of that extra electron that it actually explodes.
It literally catches fire in water.
It dances on the surface and explodes, yes.
And what about the other player, chlorine?
Chlorine is a heavy, pale green gas. It has 7 electrons in its outer shell. It's absolutely desperate for just 1 more to complete its set of 8, so it is a taker. It's actually a deadly poison.
Because it rips electrons away from things.
Exactly. If you inhale it, it violently rips electrons off the moisture and tissue in your lungs.
So you have a highly explosive metal and a deadly poisonous gas.
And you put them right next to each other. Sodium looks at chlorine and basically says, please, take this electron, I don't want it. Chlorine says, gladly, I need that. Sodium gives the electron away entirely.
A complete transfer.
A complete transfer. Now, because sodium lost a negative charge, the whole atom becomes positive. Chlorine just gained a negative charge, so it becomes negative.
And opposites attract.
Snap. They stick together magnetically with a very strong bond,
Right.
and the resulting compound is sodium chloride, table salt.
And this was the huge aha moment for me in the reading. The resulting salt isn't explosive, and it isn't poisonous. It's completely harmless. We sprinkle it on French fries. Why does the danger just vanish?
Because the chemical hunger is gone. Sodium is happy because it finally lost that annoying outer electron. Chlorine is happy because its shell is finally full. They are perfectly stable now. The explosive, dangerous reactivity was just a symptom of their empty shells. Once the bond forms, the danger totally vanishes.
That is just incredibly cool to me. 2 deadly things combine to make something essential for life. Okay, let's look at type 2, covalent bonding. This isn't a transaction, this is the sharer.
This is more like a marriage or a very tight partnership.
Yeah.
In ionic bonds, one atom gives and one takes. But in covalent bonds, the atoms kind of realize that neither of them is strong enough to completely steal an electron from the other. So they agree to share them.
Water is the classic example here, H2O.
Right. Oxygen needs 2 electrons to fill its shell. It finds 2 hydrogen atoms and each hydrogen has 1 electron. But instead of stealing them outright, the oxygen atom wraps around the hydrogens and they share those electrons back and forth. They orbit both nuclei.
So everyone feels like they have a full shell, even though they're just passing the same electrons around?
Exactly. It's a very stable arrangement.
And are these bonds as strong as the magnetic ionic ones?
Often, they are much stronger. Your entire body is built mostly of covalent bonds. Your DNA, proteins, fats, these are all incredibly stable, complex structures built on sharing electrons. Or look at a diamond.
A diamond is pure carbon, right?
Pure carbon. Every carbon atom is covalently bonded to 4 other carbon atoms, sharing electrons in this perfect, rigid three-dimensional network. That tight interlocking sharing is exactly what makes diamond the hardest natural substance on Earth.
Okay, that brings us to type 3, metallic bonding. My note for this one was just the commune.
That is highly accurate. Metals is something really weird compared to the other two. If you have a solid block of iron or copper, the atoms don't hold on to their outer electrons at all, but they also don't just give them to one specific neighbor. They release them into a shared community pool.
The sources call it a sea of electrons.
Yes. The electrons float completely freely between all the positively charged metal nuclei. They don't belong to any single parent atom anymore. They just wash over the whole structure. And this one concept explains basically every physical property of metal.
Like conductivity, electricity.
Exactly. What is electricity? It's just moving electrons.
Hmm.
Because the electrons in a copper wire are already free-floating in this sea, if you push a few new electrons in on one end of the wire, the sea just shifts and electrons flow easily out the other end.
But if you try to push electricity through a diamond or a block of salt,
Nothing happens. Because in covalent and ionic bonds, the electrons are locked strictly in place. They can't flow.
and this sea of electrons also explains why you can hammer a piece of metal into a sheet, right? Because if I take a hammer and hit a big salt crystal, it doesn't bend. It shatters into a million pieces of powder.
Right, because salt is a rigid alternating grid. Plus is right next to minus. If you hit it with a hammer and shift that grid even slightly, suddenly a positive sodium is shoved right next to another positive sodium.
Oh, and they repel each other.
Violently. The crystal literally blows itself apart along that fault line.
But metal doesn't do that.
No, because in metal, the atoms are swimming in that flexible electron grease. If a blacksmith hits a hot horseshoe with a heavy hammer, the iron atoms just slide smoothly past each other to a new position. The sea of electrons just flows with them, keeping them bonded the whole time.
They never lose their connection.
Right. That is why metals are malleable. That's why we can forge swords or draw copper into thin wires or build massive steel skyscrapers. They can literally sway in the wind without snapping.
It's wild to think that the only reason we can bend a simple paperclip without breaking it is because of a microscopic commune of electrons happening inside the wire.
It connects the microatomic structure directly to the macro function we see every day.
Speaking of the macro world, let's talk about the forms these things take. Section 3, states of matter and phase changes. I mean, we all learned solid, liquid, gas in kindergarten. But reading the sources, it's really just a measure of energy, isn't it?
It is entirely a vibration scale. In a solid state, atoms are cold and they have low energy. They vibrate, definitely, but they are locked firmly in their seats.
And then you add heat to the system.
Heat is just kinetic energy. As you add heat, the vibration gets more violent. Eventually, the atoms start wiggling out of their rigid seat. They start sliding over and around each other. That is what a liquid is.
And then you add even more heat.
The vibration becomes so intense that they break free from each other entirely and just fly around the room at high speeds. That is a gas.
But there is a fourth state, the one that usually gets left out of the elementary school textbooks, but according to our deep dive sources, is actually the most common state of matter in the universe. Plasma.
Yes. We happen to live on a very cold, wet rock, so we think solids and liquids are normal. But 99.9% of the visible universe is plasma. All the stars, the sun, the massive glowing nebulae.
But what exactly is plasma? It's not just a really hot gas.
It goes beyond gas. It is gas that has been heated so intensely or subjected to such strong electromagnetic fields that the electrons are violently ripped right off the atoms.
So the shells are just completely gone.
Gone. It becomes an ionized soup of bare nuclei and free-floating electrons. And because those electrons are free, plasma conducts electricity perfectly and responds strongly to magnetic fields, unlike normal gas.
So where do we actually see plasma here on Earth?
A lightning bolt.
Really?
Yes. When lightning strikes, that brilliant flash of light is a channel of regular air that has been superheated into plasma for a split second. Or the aurora borealis, the northern lights.
I didn't realize that was plasma.
It is. That is highly charged plasma ejected from the sun, traveling through space and slamming into the gases of our upper atmosphere, ionizing them and making them glow.
It's the star of the show, quite literally.
Very literal, yes.
Now, sticking with these states of matter, I want to talk about the transition points between them, especially what the sources call the weirdness of water.
Water breaks almost all the standard rules of chemistry. If you just follow the periodic trends, water should actually be a gas at room temperature. And more importantly, solid ice should sink.
But ice floats.
Ice floats. And we are so used to seeing ice cubes floating in our glasses that we don't realize how incredibly rare that is. Almost every other substance in the universe gets denser and shrinks when it freezes.
Right. If you drop a piece of solid iron into a vat of liquid iron, it sinks to the bottom.
Like a stone. But water expands when it freezes. The specific bent shape of the H2O molecule forces it to lock into this hexagonal honeycomb lattice when it gets cold. And that honeycomb structure actually has more empty space inside it than the disorganized liquid phase does.
It pushes itself apart.
Yes. It becomes less dense as a solid.
And why does that quirk matter so much to us?
Well, if ice sank like a normal substance, every winter lakes and oceans would freeze at the surface, and that ice would sink to the bottom. Then the new surface would freeze and sink. Eventually, entire oceans would become solid blocks of ice, killing absolutely everything inside them.
But because it floats.
Because it floats, it forms a protective insulating blanket on top of the lake, keeping the water below liquid and relatively warm. Life on Earth basically owes its entire existence to this one weird chemical quirk of the hydrogen bond.
That's amazing. And what about the salt aspect? We salt the roads in winter to melt ice. How does that actually work at the atomic level?
It's basically chemical interference. When water gets cold, the molecules slow down and try to lock into that honeycomb ice pattern. But if you dissolve salt into the water, those sodium and chloride ions get physically in the way.
They block the connections.
Right, they disrupt the pattern. So the water molecules have a much harder time finding each other to bond, which means the water has to get much, much colder than normal, well below 32 degrees Fahrenheit, before it can finally overcome the interference and freeze.
It lowers the freezing point?
Exactly. That is why the ocean can stay liquid, even when the air temperature is well below freezing.
Okay, let's zoom back out again. We've covered the atoms, the atomic bonds, the states of matter. Now we need a map to navigate all of this. Section 4, the ultimate map, the periodic table.
The grid that hangs on the wall of literally every science classroom in the world. People often think it's just a reference list, but it's actually a brilliant prediction engine.
Dmitri Mendeleev, right? 1869. The story in the text goes that he loved playing solitaire, and he organized the known elements like a deck of cards.
He did. He wrote the properties of the 59 known elements on cards, and he started arranging them by their atomic mass, but also by their personalities, how they reacted with other things. And he noticed a distinct repeating rhythm, a pattern.
But the pattern had holes in it.
It did. There were spots in his grid where an element chemically should be, based on the rhythm of the rows and columns, but no one had ever discovered an element that fit there.
So what did he do? Did he change the pattern?
No, he was so confident in the fundamental math of the universe that he just left the spots blank. He boldly predicted to the scientific community, there is an element right here that we simply haven't found yet. It will weigh exactly this much, it'll be a soft metal, and it will melt at this specific temperature.
And he was right.
He was spot on. Elements like gallium and germanium were discovered years later in different parts of the world, and their properties fit absolutely perfectly into the ghost slots he had left for them on his table.
It completely proved that the universe follows a logical, mathematical structure.
It was a triumph of scientific reasoning.
Now, there is a physical trend in the table that I found deeply counterintuitive when I was reading. As you move from left to right across any row of the periodic table, you are adding protons. And you're adding electrons. You're adding stuff. So you would naturally think the atoms would get bigger and bigger, like rolling a snowball.
You would absolutely think that.
Yeah.
But they actually shrank.
Why? How does adding more stuff make it smaller?
Remember the stadium and the magnetic pole. As you move left to right, you are adding more positive protons to the nucleus. That makes the positive magnet in the center much stronger. But you are adding electrons into the exact same outer shell. They aren't getting further away.
Oh, so the strong center pulls the shell inward.
Exactly. The stronger positive charge reels those negative electrons in tighter. So a neon atom, which is all the way on the far right, is significantly smaller and denser than a lithium atom on the far left of the same row, even though neon is much heavier.
The atomic hug just gets tighter.
That's a good way to visualize it. The hug gets tighter.
Let's do a quick tour of the groups, the vertical columns, because the sources emphasize that these columns share distinct personalities. Group 1, on the far left, the alkali metals.
Lithium, sodium, potassium. These are the desperate housewives of the periodic table.
Because of that one electron.
Right. They have that one lonely electron in their outer shell. They are incredibly reactive. You will basically never find a chunk of pure sodium sitting around in nature.
Because it would have already exploded.
Exactly. It would have reacted with the first raindrop or gust of humid air it saw a billion years ago. In labs, we literally have to store these metals submerged in jars of mineral oil just to keep them from touching the moisture in the air and exploding.
Then you move to the massive middle block of the table, the transition metals. These seem to be the celebrities.
These are the structural metals we build our world out of. Iron, copper, gold, titanium.
Let's talk about gold for a second. Why is it so historically valuable, aside from just being shiny and yellow?
From a chemical standpoint, it is valuable precisely because it is completely boring. It is chemically noble. It utterly refuses to react with anything. Think about it. Iron rusts rapidly because it reacts with the oxygen in the air. Silver tarnishes because it reacts with trace amounts of sulfur.
But gold doesn't do any of that.
Never. You can drop a solid gold coin into the ocean, leave it in a... It's virtually immortal in a chemical sense.
So we value it because it defeats time.
Precisely. It doesn't decay.
What about mercury? It sits right in this group, but it is the massive oddball.
It is the only metal on the entire table that is liquid at standard room temperature. It's weird because its atomic structure holds its electrons so tightly to the nucleus that they don't share easily with other mercury atoms. So the metallic bonds between the atoms are unusually weak.
That makes it a liquid.
Right. But it is an incredibly dense liquid. You could take a solid steel blacksmith's anvil and drop it into a bathtub full of mercury, and the anvil would float on top like a rubber duck.
That is a crazy image.
But of course, it's also highly toxic to the human nervous system, so don't try that.
Good disclaimer. Then we have the metalloids, the borderline cases on the right side, silicon, arsenic, germanium.
Economically and technologically, these are arguably the most important elements in the modern world. They sit right on the jagged dividing line between the metals and the nonmetals.
Because metals conduct electricity and nonmetals block it.
Exactly. But metalloids are semiconductors.
Which means they can switch.
Right. If you treat them right, you can make them act like a metal and conduct, or act like a nonmetal and insulate. That unique ability to switch electricity on and off rapidly to represent a 1 or a 0 is the physical atomic foundation of binary code.
So without the confused identity of silicon, we don't have computer chips.
We don't have chips, we don't have smartphones, we don't have the internet.
The entire digital age is basically built on an element that couldn't quite decide what it wanted to be.
It's a very poetic way to put it, but chemically, yes.
Okay, let's zoom out again. We have done the individual atoms, the periodic map, the chemistry. Now let's look at what happens when these invisible things build up into something massive that we can actually walk on. Section 5, from atoms to Earth, geology.
So we are moving from chemistry to geology. And the bridge between those two sciences is the mineral.
I always get this confused. What is the actual difference between a rock and a mineral?
The best way to think of it is a chocolate chip cookie. The whole cookie itself is the rock. It is a messy, jumbled mixture of lots of different things. But the chocolate chips, the individual sugar crystals, the salt, those are the minerals.
Okay, that makes sense.
A mineral is a specific, pure chemical compound with a strict formula. Like quartz is always silicon dioxide. But a rock, like granite, is just a mashed-up mixture of quartz, feldspar, and mica, all baked together.
And when those pure minerals form, if they have enough space and enough time, they form crystals.
Right. A crystal is really just the macro visible version of the atomic structure. And we talked earlier about salt being a rigid grid of alternating
With a
atoms.
plus and minus grid.
Yes. If you let a salt crystal grow very slowly from evaporating water, that microscopic atomic grid builds on itself until it becomes a visible, perfectly square cube in your hand. A crystal is just atoms arranged in a repeating three-dimensional pattern that goes on for billions and billions of repetitions.
And this is exactly where we get gemstones. I have to say, I loved the imposter syndrome section about gemstones in the source material.
You mean about rubies and sapphires?
Yes. I had no idea about this.
Most people don't. They are literally the exact same mineral. It's a mineral called corundum, which is basically just aluminum oxide. And pure corundum is actually completely clear. It looks like glass.
So why is a ruby deep red and a sapphire deep blue?
It is entirely due to microscopic pollution, impurities. If a few stray atoms of the metal chromium happen to sneak into the crystal lattice while it's growing deep underground, those chromium atoms absorb light differently. They reflect red. So the stone looks red, and we call it a highly valuable ruby.
And the blue.
If it's a tiny bit of titanium and iron that sneak into the lattice instead, it reflects blue light. We call it a sapphire.
So a priceless ruby is really just a piece of clear rock with a tiny bit of chromium contamination.
Exactly. The immense value comes from the specific type of dirt that got trapped inside the crystal as it cooled.
Speaking of crystals, we absolutely have to talk about the giant crystal cave. The visual description in the source material is just insane.
The Naica mine in Mexico. It is one of the most spectacular geological discoveries ever. It looks exactly like the Fortress of Solitude from the Superman movies.
It's about 300 meters underground, right?
Yes, deep underground. It was accidentally discovered by silver miners. They broke through a wall and found a cavern filled with perfectly formed crystals of selenite, which is a form of the mineral gypsum. But these aren't crystals you hold in your hand. They are the size of telephone poles.
The source text says they weigh up to 55 tons.
They are massive, solid beams of crystal, up to 12 meters long. You look at the expedition photos, and there are these scientists in bright orange suits climbing over them, and the humans look like tiny ants compared to the crystals.
Why are they wearing orange suits? Is it radioactive or something?
No, the suits are for the heat. The cave is an incredibly deadly environment. It is arguably one of the most hostile places on Earth. The ambient air temperature down there is over 50 degrees Celsius.
That's what, like 122 Fahrenheit?
Right. But worse than the heat is the humidity. It is 100% humidity.
So your sweat just doesn't work.
Exactly. The human body cools itself by sweating and letting the water evaporate off the skin, which pulls heat away. But at 100% humidity, the air is totally saturated. Nothing can evaporate. So if you walk in there without a specialized cooling suit packed with ice, your internal body temperature just skyrockets immediately.
How long could someone survive unprotected?
You would die of severe heat stroke in about 15 to 20 minutes.
And that intense heat is exactly why the crystals were able to get so massive, right?
Yes. For hundreds of thousands of years, that cave was completely flooded with mineral-rich groundwater, and it was constantly heated by a giant magma chamber deep below it.
A giant underground pressure cooker.
Exactly. And for about 500,000 years, the water stayed at a very specific stable temperature, right around 58 degrees Celsius. That perfect, uninterrupted stability allowed the gypsum atoms to slowly settle out of the water and stack onto the crystal lattice, layer by microscopic layer, century after century.
It's basically a cathedral built entirely by deep time and magma.
It shows you what nature is capable of building when it is left completely undisturbed for 500,000 years.
Incredible. We are nearing the end of our journey here. Section 6, mixtures versus compounds. We've used these terms a bit, but let's formally clarify the difference for the listener.
It is essentially the difference between making a salad and baking a cake.
I like food analogies. Go on.
In a salad, which is a physical mixture, you toss lettuce, tomatoes, and cucumbers into a bowl. They're mixed together, sure, but the tomato is still fundamentally a tomato. You could reach in and pick it out. The substances haven't changed their chemical identity. The air we breathe is a mixture. A rock, as we discussed, is a mixture.
And a compound.
That is the cake. You mix flour, sugar, eggs together. Then you apply heat. A fundamental chemical change happens. Covalent and ionic bonds break and reform into entirely new structures. You cannot reach into a baked cake and pull out the raw egg. It has become a fundamentally new substance.
Like water. You can't just reach in and pull out the explosive hydrogen.
Exactly. Water is a chemical compound.
And this naturally leads us to alloys. A really special type of mixture that literally defined human history.
An alloy is essentially a metal salad. It is a mixture of two or more metals. And we do this because pure metals, straight from the earth, are often completely useless for what we need. Pure copper, for example, is way too soft to make a sword or a tool. It would just bend the first time you hit something with it. Pure gold is too soft for a durable ring.
So we mix them up.
We melt them down and mix them. If you mix copper with a little bit of tin, you get bronze. Bronze is significantly harder and tougher than either of its soft ingredients. That one metallurgical discovery defined an entire era of human civilization, the Bronze Age.
And what about steel?
Steel is iron mixed with a tiny, tiny amount of carbon. Pure iron is strong, but it's very brittle. It snaps. But carbon atoms are really small. When you melt them together, the carbon atoms slip right into the microscopic gaps between the large iron atoms.
They wedge themselves in there.
Right. They pin the iron atoms in place. It prevents the layers of iron from sliding past each other too easily. That tiny addition of carbon makes the resulting metal incredibly tough, but also flexible.
And if we want to stop it from rusting, we add chromium.
Yes, you add chromium and you get stainless steel. The chromium aggressively reacts with the oxygen in the air first, before the iron can. It forms a microscopically thin, completely invisible skin over the steel that protects the iron underneath from rusting. It is basically material science one-on-one.
And just quickly, the outline mentions how we separate these mixtures in industrial applications. Because they aren't chemically bonded like a cake, we can still pull them apart.
Right, because they are just mixtures, we exploit their physical differences to separate them.
Like distillation.
Exactly. Distillation relies on different boiling points. If you have a liquid mixture of alcohol and water, like when you're distilling whiskey, you gently heat the vat. Alcohol boils and turns to gas at a lower temperature than water does.
So the alcohol turns to vapor first.
It boils off first. You catch that vapor in a tube, you cool it back down into a liquid, and boom, you have successfully separated the pure alcohol from the water.
It's just amazing to me how simple these base concepts really are. Boiling, filtering, mixing. But how unimaginably powerful the industrial applications are.
That is the whole underlying theme of this deep dive, isn't it?
It really is. So let's bring it all home. We started out looking at quarks, these tiny vibrating strings of trapped energy, and we ended up talking about 55-ton gypsum crystals and the stainless steel skyscrapers that define our cities.
It is a single, unbroken, continuous chain. The properties of the tiny quark determine the behavior of the proton. The number of protons determines the identity of the atom. The electron shell of that atom determines exactly how it bonds with its neighbors.
And those atomic bonds determine if it's going to be an invisible gas, a soft metal, or a diamond.
And understanding that specific chain manipulating that materials technology is exactly how human beings built the entire modern world.
Absolutely. From the ancient alchemists trying to magically make gold and accidentally inventing gunpowder, all the way to modern materials, scientists meticulously arranging carbon atoms to create graphene.
Graphene is actually the perfect example to end on. Because what is graphene? It is just carbon.
The exact same stuff that is in your pencil lead?
Just carbon. But it is all about how it is arranged. In a pencil, the graphite is carbon arranged in sheets that aren't bonded tightly to each other vertically. They just slide right off. That is exactly why it leaves a dark mark when you drag it across paper.
But if you isolate just one of those sheets?
If you can isolate a single layer of those carbon atoms, literally just one single atom thick, it becomes graphene. It visually looks like microscopic honeycomb chicken wire. But in that specific flat arrangement, it is 200 times stronger than structural steel.
It's the exact same Lego brick, just a different build.
Exactly. It's not about what ingredients you have. It is entirely about how you connect them.
That is brilliant. So here's my final thought for you, the listener, to take away from this. We've talked a lot about carbon, right? The graphite in pencils, the diamond in a ring, the heavy carbon-14 we use to date fossils. But think about this. Every single heavy atom in your body, the calcium in your bones, the iron in your blood, the carbon in your DNA, none of it was created here on Earth.
It couldn't be. Earth doesn't have the heat.
Right. Those specific atoms could only be forged in the crushing, unimaginable pressure inside the core of a dying star. When those stars exploded in supernovas billions of years ago, they scattered those newly minted atoms across the empty vacuum of space. And eventually, a tiny fraction of those atoms found each other, bonded together due to their electron anxiety, and eventually built you.
You are literally made of recycled star stuff.
Exactly. So the next time you drink a glass of water or type on your silicon phone or Just take a breath of oxygen. I want you to think about that invisible, frantic dance of electrons happening right under your nose. Think about the massive empty space inside the stadium of the atom. It is all happening furiously all the time just to hold your reality together.
And when you finally see it that way, that reality is pretty spectacular.
It really is. Thanks for diving deep with us today. We'll see you next time.